My name is Neha, and I'm actually a sophomore chemistry major here at UNC. And one of the biggest reasons why I want to be a chemistry peer mentor is that I want my peers to truly love, enjoy, and understand chemistry. It's easy to get discouraged at first because you feel like if you don't first understand it, you never will. But especially with chemistry, I feel like that's not the case at all. With enough resources, practice, and time, I feel anyone can be good at chemistry. And I hope to be one of the resources as a peer mentor to help peers get there. One of the biggest methods that I would recommend to my peers for studying is doing practice problems. Because chemistry may seem uh, not cohesive and random, but the beautiful thing is that there's a pattern in almost everything. And if you do enough practice problems, that's how you'll see it. So that's that'd be one of the biggest ways that I'd recommend studying. So the problem I'll be solving is a weak acid strong base titration problem. And the problem reads, calculate the pH of the solution formed when 45 milliliters of 0.1 molar sodium hydroxide is added to 50 milliliters of 0.1 molar acetic acid. So if a peer asks me for help on this problem, I would advise them to write out the reaction just to visualize what's happening. So the problem states that acetic acid and a strong base are being combined, and this would form the conjugate base of the weak acid and water, which will not affect this problem because it's a liquid. I would make sure they understand that this reaction goes to completion because the sodium hydroxide is a strong base that needs to react completely. So the first step is getting everything in terms of moles, because that will be the easiest to do and it's possible to do because we have the information for all of the reactants and products to have everything as moles. So to get the acetic acid in moles, we would do the volume times the molarity. So let's do it up here, 0.1 molar, of course with sig figs, and make sure to turn this into liters, because molarity is moles per liters. And then we can do the same with the sodium hydroxide. It ends up being 5 times 10 to the negative third moles of acetic acid and 4.5 times 10 to the negative third moles of sodium hydroxide, or just the hydroxide, and this would be 0 because we don't start off with any of the conjugate base. The change factor, we established earlier that the hydroxide reacts completely, so we know that the end product has to be 0. And this makes the change factor 4.5 times 10 to the negative third moles, because we want to get rid of all of the hydroxide. And if it's a change factor for one of them, it should also be the change factor for all the other components of the reaction. So I make sure my peer understands that, and also understands that since it's getting subtracted from the hydroxide, the acetic acid is also a reactant, so the change would also be subtracted, and then it would be added to the product. Because the product is being formed, the reactant's being used up. So this ends up being 4.5 times 10 to the negative third mole, and this would be 0.5 times 10 to the negative third mole. Now I would ask the student, my peer, what they would think of doing next. One suggestion might be to do products over reactants and equal that to the Ka value, because that's a different definition of Ka. But although that's a great method to solve it, I would encourage them to, go through it. But I would also remind them that this is a buffer problem. We have a weak acid and enough strong base to convert it to its conjugate weak base. And we know the Ka, and then we know the concentrations / moles of the acid and conjugate base. So we can use, I would see if the peer knows or remembers the Henderson-Hasselbalch equation, which is written here. So then I would see if the peer can plug in the values and get the pH. If they need help, I would tell them that the pKa, the p function, just means negative log. So the pKa would be negative log of the Ka. And just be, we have the base right here, the conjugate base, and then the weak acid would be that acid here. So after we plug this into our calculators, we get a pH of 5.70. And the pH has 2 decimal places because the Ka value has 2 sig figs, which is a rule I would remind the students of.